In section 13.1, you learned about acceleration. In 13.2, you will learn all about graphing this acceleration. You're going to see that graphs are a really effective tool for communicating information. A lot of information is contained in a graph. We're going to look first at constant acceleration. So remember that acceleration is the rate and change in velocity. So acceleration equals change in velocity over change in time. If velocity is changing at a constant rate, as represented by constant acceleration, it can be doing so in one of two ways. Either accelerating, so speeding up, or decelerating, slowing down. We're going to draw velocity versus time graphs for both of these scenarios. So on the y-axis, we're going to put velocity, and we're going to have it in meters per second, and it needs a direction, so I'm going to put forward, and have our directions as forward or backwards. On the x-axis will be time in seconds. For a constant acceleration, the velocity must be changing at a constant rate. So that would be represented with a straight increasing line. The slope of this line would equal the acceleration. For a decreasing velocity, something that is slowing down, velocity meters per second forward, and time, the slope would go the other way. It would be decreasing. So the slope of the line on a velocity versus time graph equals the acceleration of the object. If it is a positive slope, that means that it is a positive acceleration. The object undergoing the motion is speeding up. And if it is a negative slope, it is a negative acceleration. The object undergoing the motion is slowing down. So I want you for the rest of the lesson to recall that slope of the line shows change in acceleration, or change in velocity, which equals acceleration. So if velocity is constant, and this should have a little arrow over it to indicate that it's a vector quantity, if velocity is constant, then acceleration is a horizontal line. So let's do a graph of what that would look like. If we had velocity here on the y-axis, meters per second forward, and time in seconds on the x, for a constant velocity, no acceleration, will be a horizontal line. Now, you know that the slope of the line equals the acceleration. On a velocity versus time graph, you can also get information about displacement. And this is by looking at the area under the velocity time graph. You should recall that area of a rectangle or a square equals length times width. And in this case, area equals meters per second, if we have the length being our velocity, times seconds. So our area is going to be in meters. Our area is displacement. So area under velocity time graph equals displacement. So if, for example, we wanted to find how far this object could travel by this time, we would be looking at this rectangle here. Let's look at an example with actual numbers in it. So here we have an ant crawling across a picnic table carrying a breadcrumb. Okay. The ant was crawling at 6 meters per second, so a constant velocity. Using the figure below, which we need to draw, calculate the displacement between 5 and 12 seconds. Okay, so we're going to have velocity in meters per second forward here, and we're going to have time in seconds on the x-axis. Putting some values, 2, 4, 6, 8, and some values here, 5, 10, let's go like this, 15. Now this ant was moving at a constant velocity of 6 meters per second, so we just have a constant line here. Humor me and pretend that's straight. So we want it between 5 and 12. So we want this area here. So area equals length times width, meaning displacement equals velocity times time. Velocity is 6. Oh, this is centimeters. I wrote it as meters. Velocity is 6 centimeters per second. The time is from 5 to 12, so that's 7 seconds. When you multiply this out, 6 times 7 is 42, so the ant moved 42 centimeters. And because we're looking for displacement, we should put a direction, 42 centimeters forward. Velocity isn't always constant though. Velocity increases and decreases. So how can we find displacement here? Well, let's look at a graph. Here we have velocity and time. And let's say that velocity is increasing. Now, if we wanted to know how far the object has gone or the person has gone or whatever at this time, we would need to find this area here. You should remember that area of a triangle is base times height divided by 2. So in this case, it's going to be velocity times time divided by 2. An example now with actual numbers. We have a plane starting from rest and reaching a velocity of 90 meters per second west in 22 seconds. We need to draw a graph and determine the displacement. So here we have velocity, and it's in meters per second west, and time in seconds. Increases at a constant rate up to 90 meters per second. So that's here. And that takes 22 seconds. So we want this area. We know that displacement in this case is area of the triangle, which is velocity times time, base being time, height divided by 2. So it's going to be 90 times 22 divided by 2, which will work out to 990 meters west. So those are all examples of constant acceleration, either no acceleration or constant acceleration. Now we're going to look at instantaneous acceleration. So this is when the acceleration is changing. So acceleration of an object at a particular instant in time, and it's determined by calculating the slope of the tangent line. So for example, if we read this, an elevator traveling from the ground floor to the 6th floor starts from rest, accelerates to briefly a constant velocity, then slows down until it reaches the 6th floor. So what would this motion look like? In a graph, we would have velocity versus time. Starting from rest, and it's going to move slowly, and you've been in an elevator, you know it moves slowly, and then it speeds up and accelerates until it reaches some constant velocity, and then it will, or it reaches a constant change in velocity. So it's speeding up, kind of increasing how much it's speeding up, and then speeding up at a constant rate, and then it will travel at a constant velocity, and then it will slow down at a constant rate, and as it approaches the floor, it will slow down, it'll curve a bit, because it's going to be slowing down slower. So here we have, on the flat part, a constant velocity where there is no acceleration. So constant velocity equals no acceleration. Here and here, where there is a constant slope, we have a constant acceleration. This is a different constant acceleration because it's negative. And here where it's curving, we have a changing acceleration. If you wanted to take the acceleration at an instant in time, such as here, you would need to go up to this curve and draw the tangent line, and then take the slope of that tangent line, just like you did when you were taking instantaneous velocity.